Exercise 57. So let's talk about locally compact normed K vector space, where K is valuation field. So let K with some absolute value or with some valuation, okay, valuation field. And that valuation gives you norm or absolute value. And then consider normed K vector space. So with respect to this absolute value structure on K. Not necessarily, this norm is not necessarily non-Archimedean. Non-Archimedean means we require that we have a stronger version of triangle inequality. So in general, we only have, so the remark, in general, we only have we require the length of a side of a triangle is less equal than the addition of the length of the other two sides. What we want to prove is that consider the unit ball being compact. So this is a topological space with, if you want, the metric, this is metric space with distance induced by the norm. I mean, the distance of two vectors is the norm of their difference. We want to show that this is equivalent to V is locally compact. Okay, so remark. So example, if you take K to be QP, and then let's even take just V to be a normed QP vector space. Let's just take V to be one-dimensional QP vector space. If you want, just fix some bases. And then the fact that ZP, I mean, suppose with, here is the p-adic topology, the p-adic valuation, okay, and then norm you just take, again, the one comes from p-adic topology again. And then the fact that, so I would even just take the I mean, I'm not going to put anything different than just this. You could fix spaces, but then the topology I would basically just define down the coefficient. In that case, I'm really talking about this very trivial example of just taking Q itself, okay, and this norm QP vector space dimension 1. There's no difference if you just fix a basis for this one-dimensional vector space, but then I'm going to define what is my norm. I'm just going to define to be the norm on any vector of this one-dimensional vector space to be the norm on this coefficient. Right. So let me just write this. Then ZP is compact. This is our exercise 56. Implies as application of our exercise we are going to prove 7 that QP is locally compact. So locally compact by definition, it means that any point of this topological space there exists some neighborhood that is compact as a topological space. Secondly, some exercise that if you take K to be Q, the rational numbers, whatever you put the absolute value should mean p-adic valuation with p equals infinity, or p-adic valuation, then it doesn't work. Which I mean, then of course the statement here doesn't say the statement still holds, but by the fact that V is locally compact is not satisfied in this case. And so this result in this exercise will have no application in your case. In case of K equals Q. Locally compact. Or equivalently, then the unit ball. So let me just use the notation unit ball. Ball center at 0 with radius 1, and then take the closed ball is not compact. Exercise. Lastly, let me recall that in general for J topological group, by definition, so the translation or the product is continuous by definition. And then as application or as a result of this, you have at least the following two factors. The first is that this gives you multiplication by some element A in J, gives you a homomorphism, just because this is obviously bijective, because this is a group. Can we get the inverse map by multiplication by A inverse, right? and this is continuous by definition, and obviously it has continuous inverse, which is multiplication by inverse, which is again continuous by definition of topological group. The second fact is that if you have any open of G, then the map from S to coset A times S, still multiplication by A, is again a homeomorphism, and also this is a homeomorphism to write multiplication by S because this is also homeomorphic to S. Right. Okay, so now let's prove this exercise. So, by the remark 3, notice that as topological group, so for any point, any element in this topological space, if you have a closed ball centered at 0 with radius 1, then you map it to A plus 0, 1 just by multiplication, product with A, because here we are talking about this additive operation. This is homeomorphism, right? So for any element here, we just add it to A plus X. Hence, if the unit ball, so we have actually defined this, call this unit ball centered at 0 with radius 1 is compact, will imply that A plus is compact. But this is a neighborhood of A that is compact. So we have proved that this direction is true. Okay. So why this is topological group? Because, so this is firstly a K-vector space. So you have with respect to the datation, you got Z mode at least, right? This is happening group, and that the topology on this K-vector space rely this as a topological group. I mean, that's what comes from the fact that this is normed K-vector space, and it will automatically become a topological group. And then let's prove this. Other direction. So for the other direction, you just have to notice that if this is locally compact, there exists some. There exists some closed ball. Center at 0 with, let's say, radius r. Let's denote it B0R. That is compact. So let me add a condition. Let's require this is not trivial. Which means that there exists elements with its norm neither 0 nor 1. Let's take some element from this normed field K. Such that the norm or the absolute value of this K on its inverse is exactly this R, then we construct homeomorphism from this compact ball center at 0 with radius R to the ball center at 0 with radius 1, which maps, which is multiplication by K. And because we have multiplication by K, and so that's why we're changing the radius from R to 1. As we remarked, so this multiplication by element spoken K is homeomorphism. So it's not exactly the same situation as before, but again you could just check it. This is bijective. Continuous. By fact, this is normed vector space, and this inverse is continuous. So this is a homeomorphism, and so the first is compact implies that this is compact. And so we are done. So let's stop here for a while. Look at this detail that. So is y for whatever radius r positive, you could always find some element in your field K such that its radius is exactly r. I mean, it's better to see that without loss of generality. If this is compact, then the closed of compact is again closed, right? You could not necessarily exactly R, you could even put the coefficient to even smaller than R, right? Because if you have an element K with its absolute value smaller than 1, then just doing iteration on it, then this will tends to 0, and you could take element from K with its radius as smaller as you want, and then just make sure you pick an element in your field K such that its norm is smaller than that R, and that is okay. I mean, this is just a small trick. Taking it to be inverse, it doesn't matter. You could just put it here. It's the same thing. Okay. We could always find some case such that its norm is smaller than R, because if you cannot find one exactly whose norm is R, I mean, you could shrink this R to some even smaller radius. It's still compact. If that works. So what do I want to say then? As application, let's see. This is already mentioned, so ZP is compact. Implies that QP is locally compact. And this works for finite dimensional ZP vector space endowed with product topology, for example, right? And for example, this works also for GLN LCP, considered as subgroup of GLN of QP. Right. And so the topology is just product topology there. And you could have similar arguments.